Go. First one, f of x plus h minus f of x over h. So I see a rocks and I see I rocks. I see definition of a derivative. I see slope. I see slope of secant. I see derivative at I rock. I see a mix. So is it an average rate of change or is it an instantaneous rate of change? Which one is this? This is an average. Why is it an average, not instantaneous? Okay, fine.
Because if it was instantaneous, wouldn't it have to have like a limit as it approaches?
The limit, if it was instantaneous, you'd do the limit as h approaches 0, right? So what is this? This is actually just traditional slope. This is just change in y over change in x. Excuse me. So this is just slope of the secant or average rate of change. If it was slope of the tangent or instantaneous, it would need a limit in front of it. Okay, bless you. What does d dx mean when it's in front of something? It's derivative, right? So, yes, oh, very good with respect to x. So the derivative of negative 3 cosine x, be careful because the derivative of cosine is negative sine, so you get this double negative, right? So you end up with a positive 3 sine x, which looks like every single one of you got, so well done. Okay. The limit as x approaches 0 from the right of 1 over x, it helps if you know the graph. But even if you don't know the graph, you can pick a number real close to 0, like 0.1, and just see if you get positive or a negative. You get a positive. So, but if you know the graph of 1 over x, which looks like this, right, as x approaches 0 from the right, you're pointing up to positive infinity. So there was one group that said negative infinity, but it should be positive infinity. Okay. Ooh. We have some great answers for number 4. There are a lot. I don't think I had a single group in my first period who got number 4 correct. And here we have a lot of correct answers. We have some incorrect answers, but we have a lot of correct answers. Okay, so the question is, give an example of a function that is not differentiable over its entire domain. I love the absolute value of x. Nobody thought of absolute value of x in first period. This is great. So that would be a great example. Why is absolute value of x not differentiable? Because you got a sharp turn, right? Sharp turn. So it's only at 0. Right? It's differentiable everywhere else. It's just not differentiable at 0. Okay, the 1 over x is actually what everybody in first period put because you guys have just done it in number 3. So 1 over x isn't differentiable at 0, but 0 isn't in the domain of 1 over x. And since this says, give an example of a function that is not differentiable over its domain, 1 over x doesn't count because it is differentiable over its domain. Let's see. X equals 5 and x equals 0. Those are vertical lines. You're right, they're not differentiable. However, they're also not functions, right? So those would not be an example because they don't fit the requirement of it being a function. So absolute value of x is great. My favorite example for this is x to the 2/3, which also has a sharp turn. That's the bird function. Bless you. And then any piecewise function where the domain is all reals, but it has discontinuity, like a jump discontinuity, right? Then that would also be not differentiable over the entire domain. You could have a piecewise something that looks like, this, like that, right? The domain is still all reals, but it's not differentiable where you have the jump. So something like that. All right, good thinking, guys. I liked all the creativity in the answers. All right, if f has a maximum value at c, what do we know about f prime of c? So, ooh. All right, one group got it correct. And, so we had 7 incorrect answers and 1 correct answer. So, Vika, how are you? Good. What'd your group put? Right. So everyone put f prime of c equals 0. F prime does not have to be 0 at a max, right? I could have a function that looks like that,
has a max, but the derivative is not 0, it's undefined, right? Could be either or. So be careful that you don't assume 0. It could be 0 or undefined at a max. All right. So f prime of c equals 0 or is undefined. Okay. Good warm-up. Well done, guys. All right. Today we are doing kind of a combo of 2 sections. We're finishing 5.1 and starting 5.2. So this is 5.1b/5.2a. I could write and evaluate the limit definition of a definite integral. What'd you say? The indefinite integral you already know how to do. Those are antiderivatives. Yeah, those you did in section 4.9. Today is our introduction to definite integrals. Although we won't be doing so do you know how derivatives, there's a short way and there's a long way? You did a limit definition of a derivative, which we kind of led to in the warm-up, and you did shortcut methods for derivatives, right? We all like the shortcuts better because they are faster, right, and easier. Okay, so today we're going to learn the long way for a definite integral because it's going to make you love the short way so much more. Okay. So it's the hammer, right? Why are you hitting yourself in the head with a hammer? Because it feels so good when I stop, right? Okay. So anyway, today we're going to do the limit definition of a definite integral, and then you're going to love not having to do it anymore. Okay. So, all right. I actually don't mind the limit definition of a definite integral. There's a little bit of satisfaction about doing these problems, and there's some fun methods inside of them, but they are very long and they take a lot of paper. So once you learn how to do the shortcut, you're gonna say, why did we ever do this? But it's the only way that you know what a definite integral is by learning the long way, because this is how it really truly was founded and derived, right? So you got to learn the long way so you understand what a definite integral is and why does it give you area and all that kind of stuff before you get to jump to the shortcuts. Okay, so on this slide, I am going to walk you through how we derive the formula, the limit definition of a definite integral. I'm going to walk you through it. You do not have to know this, right? But it's good to get an understanding of where did this formula come from? How did we generate this, right? So I'm going to pause this for 1 second. So in order to derive the limit definition for an integral, I'm going to start by just deriving a formula to find the area under a curve using 4 rectangles. And then once we learn how we generate a formula for 4 rectangles, then we're going to learn how to generate a formula for n rectangles, and then we're going to learn how to take the number of rectangles to, what do we have to go to for exact? Infinity, right? Excellent. Okay. So we're going to start, though, with just 4 rectangles. So this, just in case you recognize it, this is the graph y equals x squared. We did this yesterday from 0 to 1 using 4. What kind of rectangles are these? Right. They're right-handed rectangles, right? Okay. So the area of each rectangle is a width times a height, right? And we already know our width. I'm going to remind you. B minus a over n. So for this problem, our width is 1/4, right? I'm just going to call the width W. So for now, I'm just know when I write W, I mean width. All right. So here's the thing. Our area using 4, so I don't know if I should put approximate because it is this implies it's approximate. Anyway, our area using 4 right-handed rectangles. So remember remember we could put the width out front. So we have the width out front times, and then we need these 4 heights, right? Height, 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 height. Okay? Does everyone remember that from yesterday? Okay. So how do we generate the first height? Well, we need a number to plug in. Here's how we find the number to plug in. We start at the left endpoint. Our left endpoint is 0. I don't want to plug in the left endpoint because I'm using right-handed rectangles. So I'm going to start at the left endpoint and add 1 width. That's going to take me to the first number to plug into my function. Does that make sense? Okay, so the first number I'm going to plug in is just f of my left endpoint plus 1 width. And I'm plugging it into the function because I need the height, right? Okay, so this is like my x value that I'm plugging into the function. So left endpoint plus 1 width. Then, I'm going to run out of space, so I'm going to do this. Okay. To get the next number to plug into my function, I'm going to start at the left endpoint and travel 2 widths. Right? So now I'm plugging left endpoint plus 2 widths into my function. To get the next number to plug in, I start at the left endpoint and travel 3 widths. So I plug 0 plus 3 widths into my function. And then the last number that I plug in, I start at the left endpoint and I travel 4 widths. And I plug that into my function. And then I stop because that's my 4 rectangles right there. So I had my width times my 4 heights. If I wanted to, are you all, is that okay? We together? Okay. If I wanted to write this in sigma notation, well, we kind of touched on this yesterday, right at the end of class, right before the bell was going to ring. So when you write in sigma notation, so this is, if you were to write all 4 terms out, every one of them would have a W. That doesn't change at all, right? The F of doesn't change at all. The 0 doesn't change at all. The W doesn't change at all. The only thing that changes is the number in front of the W. So we would have I times W or W times I. What is the first I that we plug in? 1. What's the last I that we plug in? 4. So this sum, believe it or not, gives you the 4 right-handed rectangle approximation for area under the curve. Now, technically f up, like I'd have to plug it actually into the function, which is x squared, so it'd be 0 plus wi, squared. That would be if I plugged it actually into the function, but I'm going to keep f as like a generic function so it can represent any function. Okay, so I'm going to walk you through just so that you understand. Let's think about it. Width, height, right? I'm going to label this. So, width, height. So, if I is 1, I get the width times the height of the first rectangle. If I is 2, I get the width times, and then it's 0 plus 2 widths plugged into my function, so it's the height of the second rectangle, right? If my I is 3, I get the width times f of the left endpoint plus 3 widths. That's what I'm plugging in to my function to get the height of the third rectangle. If I is 4, then my I becomes 4. I have the left endpoint plus 4 widths. I plug that into my function. I get the height of the fourth rectangle. Okay, so I end up this cute little formula here, regardless of what f is. It could be x squared. It could be x cubed minus 3. It could be sine x, right? We don't know. F could be any function. Whatever the function is, we're walking by widths to plug into the function to get the heights of all our rectangles. All right. Now, suppose we didn't want to do just 4 rectangles. Suppose we wanted to do n rectangles. Well, end rectangles, the only thing that's different would be this, instead of a 4, you'd have an end, right? All right. To make it even more generic, what if our left endpoint wasn't 0? What if it was -3 or 22 or whatever? So instead of calling it 0, let's just call it A, because A represents the left endpoint. Are you? Yes, right.
Would I always be 1?
I will always start at 1. Yes. Because you always start at the left endpoint and add 1 width, and then 2 widths, and then 3 widths. And you keep adding widths until you get to end. All right. Now, this right here is a generic formula. It's not written very pretty. We could make this. We're going to make it prettier in a second. But this is a generic formula for an N rectangle right-handed Riemann sum approximation for area under a curve. What if we wanted exact area? There's only one little thing we need to add to this, and that's to take the limit as n approaches infinity, right? So our area, if we wanted exact area, we get the limit as n approaches infinity of the sum as I goes from 1 to n of our width times f of our left endpoint plus width times I. Now I'm going to write this out nicely. There's like 14 different ways to write this. So the way you write it with like all correct mathematical notation is you have your width is b minus a over n times, I'm going to put a big bracket here, times f of left endpoint plus b minus a over n times I. So this right here, this is the formula we're going to be using all day. You will never, ever be asked to derive it from scratch. Like, no one's going to test you on how did that formula, come to be. But this is the how. So if you didn't understand the how, just try watching the video again later on, because So it's not important, but for me, I like to know the hows and the whys. So that's how. So sorry, Didi. Yes, go ahead.
So for A in the left endpoint, that'll stay constant throughout the function.
Yes. Yes. Very good question. A is always A. Left endpoint is A. And, thank you for saying that, because when I memorize this formula, I've never memorized this ever. What my brain remembers is this. So my brain thinks you have to memorize the limit as n approaches infinity of the sum as I goes from 1 to n. And then I think width times f of left endpoint plus width times I. So my brain it never remembers it with all the letters. It remembers it with words. Yeah, Jennifer.
But is this only for right-handed? Using right-handed?
Good question. So you can derive the formula for exact area under a curve using right-handed, left-handed, midpoint, and your book actually walks through multiple different ways to get, but you always come to the same formula. I think it's easiest to see visually and explain using righties, so I always use righties. But it doesn't matter because no matter what, this is exact. So it doesn't matter that we used right-handed because technically their width is approaching 0, so they're like zero-handed. Because it's really just like, basically since the number of rectangles is approaching infinity, which means the width of each rectangle is approaching a 0, what you're really doing essentially is you're just taking the heights of all these lines and adding them all together from a starting point to an ending point. This is really what you're doing, and you're getting that exact area. So, anyway, all right, and then I have a really, really stupid memory trick. When I taught you guys when I taught you guys product rule, I taught you f prime g plus fg prime, right? Remember f prime g plus fg prime, and I made you guys say it over and over, f prime g plus fg prime. For me, the 7-syllable memory thing, it just sticks. I don't know why it sticks, but it sticks. For me, left endpoint plus width times I sticks. Left endpoint plus width times I. If I can remember left endpoint plus width times I can build the rest. So the limit as n approaches infinity of the sum as I goes from 1 to n of the width times f of left endpoint plus width times I. So you have to plug left endpoint plus width times I into your function to get your height. So we're going to walk through problems like this. But anyway, either of these. Now, how do we represent this using integral notation? That's going to be on the next slide. Does everyone have these, at least this written down? I don't care if you have the words if you don't want to. You don't have to write them. Okay. So on the next slide, I have the same thing, so you don't have to rewrite because it's just the same thing. But one of the things you should know is that this formula is the same thing as this. These two things are equal to each other. So when you have the integral from a to b of f of x dx, a is your left endpoint, b is your right endpoint, f of x is the function that you're finding the area underneath. This is the same as this. This elongated S represents an infinite sum. It actually takes like this and makes it nice and cute and easy and pretty. But we're going to be doing this today. We won't actually get to evaluating definite integrals for a couple days. I want to say Monday is when we start evaluating definite integrals. So anyway, the shorthand way. We learn tomorrow we do this day, like this kind of interim day of properties of integrals. And then Friday we learn the fundamental theorem of calculus part 1. And then Monday we learn the fundamental theorem of calculus part 2, which is how do you evaluate a definite integral. Okay. So this is just notation. Now, to go from here to here is actually, it's not bad. So from here to here is pretty simple. To go from here to here gets to be a little bit trickier. Both ways get asked on the AP exam. So they might hand you an integral. This is usually multiple choice. They might show an integral and say, which of the following limits represents this integral? And they'll have 4 different big giant limit formulas set up, and you have to pick which one's correct, or vice versa. This limit would give you the same thing as which integral, right? And then they'll have 4 integrals to choose from. So they do ask you back and forth. I should also mention, all right. Okay, so before we do this, we're going to learn first how to write, this is a side step into your book. Your book is a little weird in how they present some of these problems. So I wanted to do just one of these because you're going to see one of these in your homework. They're super easy. Once you see how it works, you're going to be like, oh gosh, I wish they were all these because they're super easy and super quick. But the College Board would never ever present a problem like this. They just don't use this type of notation. So, anyway, if we have to write this as an integral, so first thing it says is express the following as an integral on the interval from 0 to pi. What are the 0 and the pi? What do those represent? Left and right endpoints. That's your A and your B. So you put 0 and pi. It always goes left to right. Whenever you write an integral, always left to right. Like bottom is your left, top is your right, low to high. Okay, we need a function. What are we finding the area under? So this problem, they're not doing it by plugging left endpoint plus width times I into a function. They're just saying x sub I. So they're saying, hey, take the limit as n approaches infinity of the first x cubed plus the first x times sine of the first x. And then if I is 2, the second x, whatever that happens to be, right? It doesn't actually calculate what each x is. It's just saying the first x, the second x, the third x. You just plug them in until you get to the nth x. So our function, when you write your function, all you do is change your x sub i's to x's, and then that's your function. So our function would be x cubed plus x sine x. Delta x in integral notation becomes the dx. That's your width. Just so you know, in integrals, when you're writing an integral, which we will, when we get to the fundamental theorem of calculus, you'll see why that delta x, the width of each rectangle, is represented as a dx, which in chapter 2, we talked, I think, for a tiny bit about how dx is actually like when you have your slope, change in y over change in x, and then you move to dy dx. Dx is actually the limit as delta x approaches 0. Same thing here. Dx is the limit as that width approaches 0, right? So it takes you from rectangles into just like single lines. Okay, but that's all there is to it. Just change your x sub i's to x's, write it down, and kabam. Okay? I'm not spending any more time on this than this. It's in your homework 1 problem. You just throw it out and you got it. All right. These are harder. And this is something you might see on an AP exam. Okay. So, again, we're going to write these as definite integrals. We're given some limit definitions. So we have to write them as definite integrals, which means we're going to have to figure some stuff out. The first one is a little bit easier. I'm going to walk you through the first one. The second one is quite a bit harder, but I want you guys to take a minute in your groups and see if you can figure it out, okay? So the first one, first of all, what's our width for the first one? 5 over n, right? Width is always in front. Width times left endpoint plus width times I, right? F of. So, okay. So that means, I'm going to just write that b minus a is 5. Because width is b minus a over n. So b minus a has to equal 5. Which is the difference from a to b. It's like the distance. From a to b, there's a distance in between them of 5. All right. What are we plugging into our function? We plug in left endpoint plus width times I. So here's width, here's I, which means this number right here has to be our left endpoint. Because we plug into our function left endpoint plus width times I. Yeah? Okay. Okay. So our a is 2. If our left endpoint is 2, and the distance between the two left and right endpoints is 5, what's our right endpoint? 7. Very good. So we're going from 2 to 7. The next question you have to answer is, what function are you plugging left endpoint plus width times I into? Yes. Yeah, fantastic. Okay. So all you have to do is replace your left endpoint plus width times I with an x. Wherever you plug left endpoint plus width times I, that's your x for your function. So what's our function here? X cubed. And then you always have to stick on a dx. That's for the width. That width becomes the dx. Yeah.
I'm just confused with the W. Like, how would you know that it was 5?
Well, it's not 5. It's 5 over n.
Okay.
W is the width is 5 over n because. So our formula, the limit of the sum of, it's your width times stuff plugged into your function. So whenever you see number over n that's being multiplied by other stuff, that number over n is going to be your width. Whatever the number happens to be. Could be 5 over n, could be 10 over n, could be 2 over n. But something when you have a number over n times and then a bunch of other stuff, that number over n is always going to be your width. Okay, so in your groups, see if you can figure out the next one. Yes, all right.
So how did can you go over again how you got A?
Yeah, so what are we plugging in? Like, you have this parenthesis here, and you have this stuff cubed. This stuff, this is width times I, right? Because we know our width is 5 over n.
Right.
Okay, so I can see this is width times I. So what do I plug into my function? I plug left endpoint plus width times I. That's my formula, right? F of left endpoint plus width times I. So my left endpoint is whatever I'm adding to this width times I that I've plugged into my function.
Okay. And the left endpoint equals A.
Yes. Yeah, because we're going from A to B.
Got it.
Yeah.
So the dx is just rotation, right?
Well, the dx technically is what you're replacing your width with. It's width technically could be written as delta x. It's change in x. So so the delta x is becoming a dx. All right. So I'm going to pause, hoping you all figured out that your width was 2 over n, right? So our b minus a, we know the difference between a and b has to be 2. A and b have to be 2 units apart. All right. The tricky part is, what are we plugging? Finding the left endpoint. What are we plugging left endpoint plus width times I into, right? So the hard part is that there's nothing that you can plug a number plus 2i over n into. There's nothing you can plug it into that will generate this. So what do? Instead, you're not plugging it into this, like some whole thing and squaring it. Instead, you're plugging it in just to this part. So what ends up happening is the cube root and the 16 are just hard-coded into the function. And all you're really plugging into is an x squared. So here's how we figure out our left endpoint plus width times I. So we figure out that something squared equals 4i squared over n squared. So 2i over n squared gives us this, right? So if plugging 2i over n generates this function, then our left endpoint would have to be 0. So we are going from 0 to 2 of the cube root of 16 minus x squared dx. It's a hard one. I know it's a hard one. This is like 4 steps up from this one. Yeah, Ari. Oh, the hands are up like crazy. Yes.
Can you go over again how you got the cube root of 16 minus x squared dx?
Okay. So the cube root is just, that's just like, this is there, right? I mean, there's nothing I'm going to do to change the cube root. It's just part of it, right? So the cube and the root, right? This whole thing, I know is going to be a part of my function, right? There's no way of getting around that. The hard part is the guts, the inside stuff. What am I plugging into to generate this thing? My width has to be 2 over n, right? So I know that somehow my left endpoint plus 2i over n, that f of that has to equal the cube root of 16 minus 4i squared over n squared. Somehow, plugging this into my function has to give me this. There's no way, if I take, like, obviously I'm squaring something, right? I could tell, like, just looking at this, oh, look, I'm squaring my width times I, right? So, but you can't just square a part. You're plugging this whole thing as your x in your function, right? So if I have some number plus 2i over n squared, there's no way you're going to spit out a binomial with a minus in between. We know that this is a difference of squares. Like there's no way that this would ever factor into something like this. It just doesn't work. So instead, the 16 has to just be its own thing. It's not a part of your input variable. It's occasional. It's really okay. So anyway, because of that, we have to be just plugging this to generate that guy. And so then if we're plugging it in to generate that guy, A has to be 0. I know. It takes a lot of high level thinking.
Where have your problems on the AP?
Honestly, I don't know. I don't know. Yeah.
Like the only thing I don't get is how do you detach like the 16 from the
Well, a function could be anything, right? I mean, a function is a function. So, if just because I have a number here doesn't mean that that number had to originally be an x. It could just be the number, right? So you don't have to have x's everywhere. You could just have 16 minus something squared. Yeah.
Can you do the same with the first problem and say 2 plus x cubed and have it start at 0?
If we did that, so let's see. So if we had our width be 5 over n, our left endpoint was 0, so then we would have 0 to 5 of 2 plus x cubed dx. Yes, that would be the same. Now, why is that the same? Because when you do what's essentially a horizontal shift to your function, so do you guys know like to go from x cubed to x plus 2 cubed, you're shifting your function 2 places to the left. So what happens when we shift 2 places to the left? So if we do the integral from 2 to 7, or find the area under x cubed from 2 to 7, that would be the same as finding the area under that function shifted 2 places to the left from 0 to 5. So yes, you could do that. You get an equivalent, yes.
Would either of those or would both of those be acceptable? Or
Yeah,
would you-
absolutely. Yeah. So yes, good question. You can technically shift this however you want, right? This would actually be equal to x plus 8 cubed, and then I just shift this 8 places to the left, right? So yes, there are equivalent answers. This is a very good question. All right, let's move on. Now, your book does this little side step. We're going to take a second and do a little side step before we get into real problems. We haven't actually started problems yet. I know it feels like we have, but we haven't. So the book does this little side step to talk about what a definite integral is. So a definite integral, when you're looking at the integral from a to b of f of x dx, what it gives you is the area under the curve f of x, from starting at x equals a and ending at x equals b. However, it doesn't truly give you that. It's like a mirage. So what it actually gives you is what we call the net area. It gives you a net change. What the heck is net area? Well, the oopses come in when your graph looks like this. So what ends up happening is if your graph falls below the x-axis, the integral is going to spit out a negative number instead of a positive number. So if I wanted, say I asked you, hey, what's the actual total area between this function and the x-axis? You would have to split this and do an integral from here to here, plus an integral from here to here, and times it by -1, plus an integral from here to here to get the total area. Because if you were to just do the integral from a to b, it's going to do this positive plus this negative plus this positive, and technically you can have an area of 0. So which isn't really the area, it's just the integral value. All right, so anyway, so what they're trying to tell you here is that when you have an integral, it doesn't truly give you area unless the whole function's above the x-axis. If any of the function falls below, it's going to spit out a negative, and if you have part above, part below, then your integral is actually going to be the positives plus the negatives, and you're just going to get this random net area. Yeah, Costa. Yes, but doing an integral of an absolute value, what do we do with every absolute value function? Piecewise, which is going to end up spitting out these, values anyway when you split your function up, and it's going to force you to do the multiple integrals. So, but if you have a calculator, then you could just put absolute value around it and be good. So next week, we are learning how to use our calculators, right? So next week, it's either Wednesday or Thursday, I have to look, is calculator day, and we're going to do all applications. You're thinking, why would I ever want this number? Like, if this, just pretend this area is 3, and this area is 5, and this area is 3, right? So I get this integral value of 1. Like, what does that even mean, right? It's just this random number. Has no meaning at all. Actually, in context, it has tons of meaning. So when we do applications, you're going to find all kinds of meaning associated with the value of the integral, and the fact that it gives you the net change is actually a good thing. So anyway, that's just a little sidestep. Doesn't really have anything to do with what we're about to do, but this is when the book chose to teach it, so this is when I'm showing it to you. We'll do more of this as we progress further in. However, the first problem, we are going to end up with a negative answer, that's probably why they're showing it to you now, is just to justify so that you don't freak out when you get a negative answer. Okay, here we go. First example. I am going to walk you through this slowly. We're going to do this together. Don't jump ahead. These are big, big problems. Oh, shoot. You guys at the end of class yesterday did not write down those formulas, did you? All those summation formulas? No. Okay. So before we do this problem, I mean, it's okay if you wrote it down, but before we do it, where did I put my other? Oh, wait, here, I could do this. Look. Okay. Oh, here we go. So in order to do these problems, you have to know some summation formulas. Oh, wait, that's too big. Come on, go back. Come on. There we go. All right, that's as big as I can make them. All right, so the first two aren't really formulas. They're more just properties. So the first one just says if I have a sum of a constant times a function, I can just take the constant and put it in front. So, because the constant would be multiplied by every single term, so you're essentially just factoring it out and sticking it in front. So the first one's a property. The second one, the sum of the sums, is the sum of the sums. So the second one, we'll use all of these. We're going to use all 6 all day. It just means you can split up your sum. So if I have the sum of I cubed plus 7, I could do the sum of I cubed plus the sum of 7. 3 through 6 are formulas. The sum of a constant is the constant times n. All of these, if you notice, are the sum as I goes from 1 to n. So it's a good thing that that works because that's part of our exact area formula. This one right here, that's the one that Gauss invented when he was 8. Yeah, Costello. So it means the ith term. Do you when you were doing sequences in series in the last couple of years, did you have like a sub n? And you were talking about like the first term, the second term, the third term, the nth term. So I means the same thing. It means the first term, the second term, the third term. It's just whatever value you have. C is a constant. This formula right here, I had to do a presentation when I took a if you ever have an elective and you're like looking for a good elective to take, math history is really fun. I was thinking about, I don't know, like if we ever wanted to expand our math program here, like we're starting to come up with new different math classes. I was thinking about asking Mr. Virgin if we could add a math history elective and have it count as either a math course or a social studies course, like get students could choose which, like, where they needed credit and have it count for either one. So I don't know, but I don't have time right now to write that whole curriculum, but I loved that course when I was in college. It was so much fun. And boy, do you have such a much deeper understanding of all of your math when you start learning the history of how everything came to be, right? So anyway, but that formula, I had to prove it. Like, I had to derive it in front of my math history class on a little overhead projector with transparency slides. I remember doing that, deriving that formula. But it's real easy. It's just a math induction formula. Okay. And then some of IQ. All right. Does everyone have all 6 of these down? Oh, no. Okay. So when you are writing these using the limit definition, whenever you do these problems, you always want to work vertically. Line your stuff up. If you are messy or disorganized, this is not the time to be messy or disorganized. This is the time to be neat and methodical. All right? You need to write and work these problems vertically. Oops, I just tapped the word and put a little mark. Okay. Every single time you start these problems, you're going to start with the limit as n approaches infinity of the sum as I goes from 1 to n. Now we got to figure out the guts of our limit. So the first thing that you're going to want to find is your width. So what's our left endpoint?
0.
What's our right endpoint? 3. So our width is 3 minus 0 over n, or 3 over n. All of your widths for these will have an n in them on the bottom. So our width, 3 over n. Now you have to write f of left endpoint plus width times I. The thing that most students forget is the f of. So here's my recommendation for the f of, is you write your function, but you put big parentheses wherever you have an x. So you have something cubed minus 6 times something. So you write your function, but you replace your x with these big open parentheses. What goes in the parentheses? Left endpoint plus width times I. So our left endpoint is 0. So our left endpoint plus width times I is 0 plus 3i over n. So you just have 3i over n in both of these. Now you're set up. No, now we got to do it. Yeah. Okay. So, yeah, Kasia. With big parentheses, and then inside the parentheses, so left endpoint plus width times I. So it's your A plus your W times your I. So we have 0 plus 3 over n times I, which is just 3i over n. And that's what goes into all those open parentheses. Okay. All right. Any other questions? Oh, yes. Yeah.
So like the formula, when like it's the full formula,
Uh-huh.
it's f of like a plus width times I.
Mhm.
But when you're actually solving the problem, you don't write that. You write the actual.
I actually put the stuff in. You can write the formula above if that, and then fill in. That's fine. You just got to remember it's f of. F of means whatever your function is, right? Okay. All right. First thing you do. So you do the second step when you're doing these. There's 2 things that you do. So everything that's in your sum is a constant if it's not the letter I. So everything that's in here is considered a constant unless it's the letter I. Even n is considered a constant in the sum because n is just your upper bound. So this 3 over n, this width, that can go in front. Then you write your sum, and you start cleaning up what's here. So I'm going to go ahead and clean up the guts. So I have 27i cubed over n cubed minus 18i over n. So my second step, I always do two things. I move the width in front of the sum, and I start cleaning up the, I don't know what this is called. I know it's the integrand when it's there. The summogrand? I don't know. I don't know what it's called. That's it. I don't know. The argument of your sigma. All right, so that's step 2. Step 3. Step 3 is to split up the sum. So you want each of these little terms to have its own personal sigma. If you're not good at writing sigmas, you're going to be practicing a lot. So all I did was just kind of, you're not technically distributing the sigma, but I break up the sum, so each term gets its own sigma. Now, personally, I tend to actually go from here to this next step all at once, but because it's our first time walking through, I'm going more step by step. So the next thing, I don't know what that is. Is that out in the hall? Is there an alarm going off? Is it like an Amber Alert or something? Anyway. Okay. Each of these constants now can go in front of their own personal sigmas. So the 27 over n cubed, whoops, I wrote down. 27 over n cubed can go in front of its sigma. And the 18 over n can go in front of its sigma. So all I'm doing now is moving the constants for each sigma in front of their own sigma. I is not a constant. It has to stay to the right. But all the other stuff can go to the left. I did feed. Okay. Once you have it down to sigmas with i's, you are ready to replace those with the wonderful formulas you just wrote down. So let's rewrite. Don't notice I'm rewriting my limit every time, right? Notation. We grade notation. All right. So this first one, 27 over n cubed times the sum as I goes from 1 to n of I cubed is n squared times n plus 1 squared over 4. You will have to know these. Yep. Okay. Minus 18 over n times. So now over here we have the sum of I. The sum of I, that's the Gauss formula. N over 2. Okay. We're good so far, right? We're crushing it. Okay. Now some of you might be tempted. Yes, sorry. Yeah. Here. Wait, what? Okay. So here we're at the phase now where we're going to find the limit. And here is my gift to you. It's really not mine, but the limit as n approaches infinity limits at infinity involve horizontal asymptote rules, right? Our variable is n. Remember that if the degree, top and bottom, by the way, these are all polynomials. If the degree, top and bottom is the same, your limit is just the quotient of the leading coefficients. If the top is bigger, the limit goes to infinity. If you had one of these that equals infinity, it means that the region was unbounded. So you had some like vertical asymptote or something where it just went to infinity. Or if the bottom is bigger, the limit goes to 0. How could that happen? If you had like the same area above and below, right? Then you'd have a net area of 0. So anyway, but most often you're going to have the same degree top and bottom because most of the time when you're doing area under a curve, you're going to end up with some number, right? Okay. So I never sit there and distribute everything out. But you got to remember that this 3 over n is being multiplied to both of these terms, okay? So keep that in mind when you're doing this. So look at your first term. What is the degree of the n's on top? 4, because you have an n squared and an n squared. The degree is 4. What is the degree of the n's on the bottom? 4, because you have an n times an n cubed. Does that make sense? Same degree top and bottom, it's the quotient of the leading coefficients. The leading coefficients would be whatever number is times your n to the 4th on top, and whatever number would be times your n to the 4th on the bottom. So without actually multiplying it out, you have something times something on top. What have you got?
3 times 27.
3 times 27 over 4 minus. All right, let's look at the second term. How many n's do we have on top? 2. Degree is 2. What about on the bottom? 2, because you have an n times an n. Same degree top and bottom. What's the coefficient on top? And you can say something times something.
3 times 8.
3 times 18 over, what's the coefficient on the bottom? 2. So your area, which really isn't area, it's net area. So you have 81 fourths minus 54 halves, or 108 fourths. Let's see, negative 27 fourths is the area of this region. So technically it's the net area. Why did we end up with an area that was negative? Because there was more area on the bottom than there was on the top. So this is the actual graph of that function from 0 to 3 that we just did. And if you were to actually look at it, you had more stuff below than above, so you end up with this negative number. Okay? All right. Are you ready to try one yourselves?
No, but we'll do it anyways.
I think you are. All I want you to do, I'm going to give you a hint. The first thing you should write is a limit. You're welcome. Okay, right? What's the next thing you should write? Sigma, right? As I goes from 1 to n. All right. Now we need width. What's your A? What's your B? 2. So your width, which is B minus A over n, 4 over n. Did everyone get a width of 4 over n?
Yes.
All right. Woo! Okay, so that's the next thing we write is the width. The next thing you write is you copy your function and you put a big parenthesis wherever you have the x. What goes in the parenthesis? Left endpoint plus width times I. How did you do? Got thumbs up? Okay, that's like 70% of the work.
Yeah.
Yay. From here on, it's all like algebra. Okay. So from here on, the next thing that you're going to want to do, step 2, is always to move the width in front and clean up your function. So everyone take a minute and clean up the function. Are we all at the same place? All you look stumped. Did you square the binomial correctly? No? Okay. Mihika, how you doing? Has everyone figured out their little algebra mistakes and cleaned it up and gotten to this point? Okay. All right, so the next thing we do, rewrite your limits, rewrite your width. Okay, it's time to split up the sum. So what I like to do once I start getting comfortable with doing these is I like to go ahead and put the constant in front of each sum and split the sum all in one step. So I would write this as 16 over n times the sum as I goes from 1 to n of I minus 16 over n squared times the sum as I goes from 1 to n of I squared. So you're just putting the constants in front and splitting up your sum. I like to do it in one fell swoop. Once you have sums with i's, that's when you are ready to replace those with your formulas. So take a minute, replace those with your formulas, and then see if you can find your final area or net area. Did you? All right, let's take a look. It could be 64 thirds. I might just be remembering wrong. All right. So 4 over n times 16 over n. Okay, sum of I is n times n plus 1 over 2 minus 16 over n squared times sum of I squared. This one's fun. N times n plus 1 times 2n plus 1 all over 6. All right, be careful. So the first limit, we have an n squared over an n squared. So you have 4 times 16 over 2. The second limit, you have an n cubed over an n cubed. Your leading coefficient is 4 times 16 times 2 over 6. Does everyone see where this 2 came from? Yeah, because if you were to find the coefficient of your n cubed, that 2 would be there. All right, so what do you end up with? So this is 64 over 2, so 64 over 2 minus 128 over 6, so times 3, 180, 192 over 6. 92 over 6 minus 128 over 6, which is 64 over 6, which is 32 thirds. All right. So the bell is going to ring, which is a shame because the last problem I had for you guys is the most missed multiple choice problem on any AP exam ever.
Oh, gross.
Take a look at it for just a minute. The bell's gonna ring. See if you can come up with an answer.
No.
No.
All right, guys, we'll do 1 and 4.
I would say it's
What is that? Always see.
All right, give me an answer. What do you guys say?
E.
E. C. E. E.
C.
C. E.
Following students, please come to Student Center East Counseling
No
Office.
idea.
Rebecca
The
Strait,
answer.
Haley Munger,
The answer.
Mark Carr,
Oh.
I'm sorry, what?
Because this is a width of a rectangle. This is an approximation. You want an exact area? There are no rectangles anymore. We don't even need a width, right? So you got, yeah, it was a trap. Yeah, I know. Thank you guys. You guys are wonderful today. I know it's a big lesson. Thank you.
I have a question on